to bodies of water or whatever. One of the students in the previous section mentioned, she mentioned the whole idea of cohesion and adhesion allows for things like capillary action in trees and plants. They don't have a pump that can distribute the water through their bodies. So one of the properties of water, allows for capillary action to occur in plants. Any others? Did you have an idea?
This might be a stupid answer, but
No answers are stupid.
The movement of water, whenever it's in its water, the solid state or the liquid state goes down, and then the gas goes up, and it's essential to the water cycle.
Yeah, exactly. That's true. And you mentioned movement of water. We have amazing possibilities of harnessing that movement to generate energy, for instance. We could harness the change in density within a water column. We could harness the power of tides, that sort of water movement. So that's a great answer. I mean, not stupid at all. That was good. It was really good. Any other ideas? Yes, sir.
Because water is a universal solvent, it allows for animals to use bodily fluids and transport different nutrients and whatnot through their system, which other things couldn't do.
Exactly. Yeah, they barely touched on that in that. There's a lot more to that story than they mentioned. Yeah, that's really good. That's true. Any other ideas or suggestions or creative thoughts? Okay, so we're just going to leave it that water's pretty amazing, right?
Yeah.
Okay, and certainly it's essential for life as we know it. There are other life forms. There could be other life forms that aren't based on water, but ours certainly is. Okay, so now, let me give you all some handouts. So I want each team would take, there are 2 handouts, so each team please take one of each of these 2. So I'll start with you guys, and you just pass them around. Oh, you already have the answers. And also on your, looks like the other team's left. Actually, I'm sorry, there are 3 handouts that each team needs to take. One is a study guide. You answer all the questions on that study guide, you're going to know your stuff. The other is just a water cycle diagram that is your quiz for the day. And then the other is just some of the slides that will be in the Salinity PowerPoint. The other thing to know is that each of your teachers has access to a PowerPoint study guide. So talk to your teachers and they will give you the PowerPoint that we developed as a study guide. Okay? And it has a lot of useful information that we'll draw from when it comes time for the test. Okay, so one of those things that I handed out was a water cycle diagram. Things that I want you to notice is that there are 3 arrows going in 3 directions. Some are going up, some are coming down, and some are going sideways. Okay, so the ones that are going up, what's happening?
Evaporation, yeah.
We're going from water to vapor, right? Liquid to gas. So in this case, we're seeing water going up from the oceans. So obviously, what's that going to be? That's evaporation, right? Oh, look at this next one. Water going from plants into the atmosphere? What's that called? Evapotranspiration. Ooh, that's a big word. So, can somebody tell me what that's all about? Yes, sir.
So when the plant is photosynthesizing, water is brought up to the leaves, and with capillary action and adhesion or cohesion, the water molecules, as they evaporate off the plant's leaf, will pull more from down below, and then just keep going off, and as water is a byproduct, and it goes out to the atmosphere as gas.
That's a great description. Did you guys catch that? That was awesome. So yeah, that's transpiration, and then eventually into evaporation. Okay, so where any other upward arrows? Here's one. This is fresh water. So, no, this is just evaporation from freshwater bodies of water. Okay. What other ones? How about this one? This is strange. This one.
That's yeah. The top one is what is it?
So these are some that I had to look up.
Yeah.
I wasn't sure what sublimation and desublimation is. And I think I know now. When you have, probably a good example would be in the Mount Everest, let's say. Mount Everest, lots of snow and ice, lots of sun, and lots of wind. Okay? So the wind coming across and the sun action forms ice crystals that turn into vapor, water vapor, okay? Or it's more like, it's almost like ice vapor. Okay, so that's sublimation. Desublimation is the opposite. You know, you're going from the vapor, you're turning water vapor or ice vapor into, into water. So you're going from a gas to a liquid, whereas the other one is going from a liquid to a gas. But in this case, in both cases, it has to do with ice. So you're going from the solid to the vapor, vapor to the solid, whereas evaporation obviously is liquid to vapor or liquid to gas, and vice versa. Okay, so I think we got all the upward facing arrows. How about the downward arrows? How about these arrows here? What are they? What are they indicating?
Snow melt.
They're indicating smelt. Okay? And so there are two arrows there.
One is snow melt, one is stream flow. Wait, no.
How about one snow melt, one just plain precipitation? What do you think?
Yeah.
Except there's only one, there's only space for one in that box. Which one is it? Snow melt.
I think the one.
Okay, where's our precipitation arrow? There it is.
Yeah.
Okay, there's our precipitation. Here's our snow melt. Okay, where's any other downward? How about this one?
Where?
This arrow sort of going down.
Stream flow.
Stream flow. Okay, good. Now we come to the sideways moving arrows. So how about this one? We haven't done this one yet. Infiltration. Water going into the soils. Okay? And then, how about this one? This is sort of a sideways mover. Groundwater flow. Excellent. And then this little guy here, what's this little guy?
Surface.
Seepage. So what is that? Is that
It's water.
that water going into, or groundwater going into aquifers? Or
Groundwater
Like
coming up into the
coming up? Okay. Okay.
yeah, in the spring.
Okay, excellent. Okay, and then this one up here is sort of goofy.
Volcanic steam?
Volcanic steam. not goofy, it's just sort of obscure. So there's one word, somebody mentioned earlier, that there's one ION word that maybe should be on here.
Ion?
And it was percolation. Think percolation.
This one,
Is that, what did we call this one again?
infiltration.
Infiltration. So that's the same thing, don't you think?
Yeah.
Just a different word. Okay.
You do the one under the sunshine.
Hmm?
You do the one under the sunshine. Box under the sun.
What's that one?
Condensation.
Condensation, thank you. Okay, so that's forming clouds. Is that what condensation does? Okay, good. We forgot that one. Okay, so here's just a little groundwater story for you all. So, and we're sort of bringing it closer to the bay now. So for many years, I worked on a project that was looking at the health of the bay, the water quality of the bay, and once again, one of the main sources of forms of pollution is nutrient pollution in the bay. And for a long time, while I was working on this project, this was a big question mark. How much nutrient was entering the bay in groundwater? And so the USGS, the United States Geological Survey, spent years studying this over on the Eastern Shore. And the Eastern Shore is probably a really good place to study this because the main source of nutrient pollution on the Eastern Shore is agriculture. So you spread a lot of fertilizer on your farm fields, you raise a lot of chickens, the manure gets spread on the farm fields. So there's a lot of infiltration, if you will, of nutrients into the groundwater. So what these studies found out was a couple of important things. The Eastern Shore, once again, probably more so than anywhere else in the watershed, had probably one of the highest amounts of groundwater nutrient impacts. So they found out that about 20 to 30% of the total nutrient load coming into the bay was from the groundwater over on the Eastern Shore. So the groundwater coming into the bay has a lot of nutrients in it over there. And then the other thing that was really interesting that they found out was that there's a time delay, there's a lag. You apply fertilizer on the field, it's going to take 10 years for those nutrients to get transported through the soils, groundwater, and then have the groundwater make it into the bay. So it's sort of like a time release mechanism. And one of the things that we did in this study was we were trying to figure out whether the quality of water in different parts of the watershed was improving or not. Because we'd put all these controls on sediment and nutrient pollution. And for the longest time, we were seeing improvements on the western shore of the bay. But we weren't seeing improvements on the eastern shore, on the rivers on the eastern shore. And part of the reason was this time delay. You know, if we took controls, put major controls on fertilizer applications, it would take us 10 years to see the results, or start seeing the results. So, you know, once again, for a long time we didn't see any improvements, but now we are. We're starting to see improvements in the water quality of the tributaries over on the Eastern Shore. So, just a little side story there for you. Okay, any questions? But remember, this is an incredibly important, almost as important as the properties of water, is how this whole thing cycles. So here's a question for you. Was there more water on this planet centuries ago than there is now?
No.
Why do you say yes?
I did not say this.
I mean, it's pretty much a big recycling thing, isn't it?
It's just
Yeah, it's not as much ice now as, as there used to be,
Well, there's
although,
tiny bits of water coming in from meteorites, but that's it.
there you go, there you go. So it's an amazing process of continual recycling and reformation, and, you know, it's a pretty amazing thing. So, any other questions, comments? Okay, so now, let's get closer to home and start looking at where we are, what's around us. Okay, so two terms, watershed and estuary. Watershed, what's a watershed?
It's the water
Wait, then
coming
let somebody else.
from the high point down into the ocean.
So the watershed is,
It's where the water's coming from,
that comes into,
the bay.
okay. So what you're saying is this big shaded area, green area, all the water that falls in that area is ultimately going to end up
In the bay.
in the bay or in the groundwater? Right. So it's a huge area, 64,000 square miles, multiple states, urban areas, lots of farmland, and there's a mountain range that runs through part of it. So what is the major artery that, okay, no, before we go there.
What's the biggest river?
Estuary. What's that one mean? What's an estuary? What's the definition?
Water,
It's where
fresh
there's water.
fresh meat.
Semi-enclosed, okay, that, yep, there's a mouth here, so it's not fully enclosed. And saltwater and freshwater, okay, so the fresh water coming within this area ends up in the bay, and the salt water moves in from the ocean at the mouth down near Virginia Beach.
Yeah.
Okay, good. Now, what is there's one artery that is the prominent supplier of fresh water to the bay. Does anyone know which one it is? Yes, ma'am. Yes, the Susquehanna River. It's this big one that you see going through a good part of the northern part of the watershed. Okay, and then there are other major tributaries that come into the bay, and all of those major tributaries are on the western side of the estuary. The Potomac, the York, James, Tucson, Rappahannock. So all of these major tributaries are over on the western shore. And there are also a number of urban areas over on this western shore. DC, Baltimore, Norfolk being the prominent. Richmond's pretty big down here. So this part of the watershed is primarily supplying water and nutrients from agriculture. This part of the watershed, a lot of the nutrients are from man's activities, sewage treatment plants, automobiles, power plants, stormwater runoff. And then this little area over here, the eastern shore, small tributaries that receive most of their nutrient supplies, nutrient pollution from agriculture, as we mentioned. So it's an amazing body of water. There's a huge number of different animals and plants that can live within different parts of the estuary. And we'll look at that in just a minute, the major salinity regimes. This area up here is relatively fresh. In the upper parts of the tributaries, you have tidal fresh areas. And this part down here obviously is high salinity. And then you run the full gamut of salinity in between the head and the mouth. Amazing body of water. Very shallow, per se, you know, it's pretty amazing body of water. Yes, sir?
Isn't that the largest watershed in the world?
The largest watershed in the world.
I mean, like,
It's the largest estuary in North America, and I think it's the second largest in the world. I don't know about the watershed, though. That's a good question. It's one of the, if it's not the biggest, it's probably the second biggest.
Yeah.
Because that's, I mean, we're the second biggest estuary. I would imagine that the watershed is up there, too. Good question. Okay, so let's go on to this diagram. This is more just showing you, once again, estuary is where salt water and fresh water come together. But what this is showing is there are a lot of different types. You know, we like to categorize things. And this is a type of estuary called a salt wedge estuary. And the wedge is this salt. You can see the wedge here. It narrows down and then ends. And it ends largely because of the bathymetry of the body of water, the bathymetry of the bay. There's a sill up around the, I think it's a little bit above the Bay Bridge, where, you know, you have deep water and then you have a sill and then it's considerably shallower when you get up in the northern part of the bay. So this salt wedge estuary is just a particular type of estuary, and there are many like it all over the world. Ours is by far the most dynamic, though. Freshwater moving south. Remember, the bay is largely a north to south oriented body of water. So the river water is coming down and moves towards the mouth. So that's north to south. The salt water comes in from the south and migrates north. So you have basically two rivers of water, one salt on the bottom, one fresh on the top, and they're moving against one another. It's a very important physical feature of the estuary that has a lot of repercussions to the health of the bay. We won't get into that, but it's a very important feature of the bay that causes problems with dissolved oxygen and stress on animals and so forth. Okay. Now here is the typical categories of salinity that we find in the bay. The blue is the highest salinity. By the way, what is the salinity of seawater? About 35, yes. So out here, we're probably in the low 30s out here because we're close to the bay mouth. So the blue area is what's called the polyhaline region. Polyhaline is salinity greater than 18. And what's the unit that we measure salinity in?
Parts per thousand.
Parts per thousand, ppts. Okay, so the polyhaline, 18 or greater. And then this really expansive area called the mesohaline part of the bay. And those salinities are between 5 and 18 parts. Brackish water. It's all pretty much brackish to a certain extent. And then, so look at the area of the mesohaline encompasses. And that's partially because it's such a wide salinity category, 5 to 18 parts per thousand. And then the yellow areas, you're getting less and less salinity. 0.5 to 5 parts per thousand is the oligohaline. And then there are parts of the estuary that are devoid of salinity. They're what we call the tidal fresh area. And you can see the upper parts of some of the major tributaries have tidal fresh regions. There's one little tidal fresh area over on the eastern shore in the Nanticoke River. So once again, there's another feature over on the western shore called the fall line that has to do with the topography going from one land type to another. We're coming down into the Piedmont at the fall line, an important feature over on the western shore of the bay. Okay, so there is your typical salinity map. But with the bay, nothing is typical. Okay, before we get into that though, let's look at water coming into the bay over the typical, seasonally or monthly. What is the typical flow pattern coming into the bay over the course of a year? So the red line is a 72-year average. So you can see that the highest amount of fresh water coming into the bay is in the spring, March, April, May. The lowest in the summer. So it only makes sense. In the spring, we're getting a lot of rainfall, we're getting a lot of snow melt. That fresh water is coming down the rivers into the bay. As you go into the fall and into the winter, we get more and more fresh water coming in because of higher precipitation. So here's your typical pattern, but you can see 2016 and most every year doesn't really fit your typical pattern necessarily. Look at February in 2016, huge amounts of rain compared to the norm. April of 2016, considerably lower amounts of fresh water coming into the bay than the norm. So once again, you have your typical pattern, the red line, but there's almost every year you're going to have considerable variation from your typical. And once again, here is a typical seasonal pattern of salinity in the bay. When you're getting most of your highest amount of fresh water coming in, the dark blue is the low salinity areas. There's considerably more dark blue on this left map, the spring map, than the other two. There's considerably more light blue, which is the next lowest salinity. So you can see that the pattern of salinity distribution in the bay changes from season to season. Summer, when you have the lowest amount of fresh water coming in, you've got an expansive high-end salinity area. And in the fall, when you haven't had any precipitation all summer, and you're getting just a little bit in the fall, you've got a much more expansive high salinity region than even in the summertime. So, this is a living body of water. And the salinity, looking at just salinity, shows you how it's changing. It's sort of like a breathing organism that, has differing amounts of fresh water flowing through its veins at different seasons, and it changes from year to year, which this next graph shows. So here's a really long period of time that we're looking at. We're looking at 80 years worth of fresh water into the bay data. The blue, obviously, really high flow years. The red is below your normal flow pattern. The normal flow is, somewhere between, those two lines. So look at the differences between years. Look at these 4 years here. Look at how low the flow was. We were in a severe drought during that period. What do we notice? From 1970 until the present. So that's 50 years. Do we notice a pattern in those 50 years compared to the previous 20 or 30.
A lot more above average years.
Do you guys agree? Doesn't it seem like we're getting a lot of high flow years over the last 50 years? I mean, you know, there's a lot of debate about climate change, and I don't want to get into it, but one of the things that they talk about climate change in our area is that we're going to get more severe, frequent storms. Frequent, severe storms means more rainfall or snow, depending, more precipitation. So, I mean, granted, this is just one little small piece of possible evidence that says that things are getting wetter in our area. And whether it's just a normal cycle or whether it is related to climate change, if you believe in climate change, it certainly looks like there is higher amounts of fresh water coming into the bay during these last 50 years. Look at last year. It was the highest ever during this period. We had the highest amount of fresh water coming into the bay last year, this year and last year for any 2 years, except for just these two might be comparable, these 2 years. And what we notice as a consequence of all this fresh water is that things change in terms of the biology of the bay. And one of the things, we'll talk about that on the next slide. So here's a closer look and a more condensed look. So this is a 10 or 11 year period right in our, down on the dock here at the lab. And what I'm trying to show you all is the seasonal variability and the interannual variability between salinities at this one location. Here's Hurricane Irene back in 2011. That's the lowest recorded here at the lab. It was just a little bit above 4 parts per thousand. 4 parts per thousand compared to over 16. So, we get these amazing swings in the amount of salt in the water. In any location in the bay, almost any location in the bay. But when you're in the middle part of the bay, like we are, you're going to see the widest swings of salinity. So, here are the last 2 years. And the low points of these 2 years were during the summer. Okay, so the weird thing, and this sort of ties into now the biology, how the salinity affects the biology. Last year, there were no sea nettles in our waters. The first time I've ever been able to swim, and I've lived here since '84. First time I've ever been able to swim without having to worry about it throughout the whole summer. What the hell was going on? Why weren't there any sea nettles? The salinity was so low. So here is a story, and I've probably told this one before, but I'm going to tell it again. The way that this whole sea nettle thing works, there's a cool story behind how we found out that this low salinity might give rise to no sea nettles. So there was a guy, he wasn't old at that time, but he became old. There was a guy named Dave Cargo who worked down at the Chesapeake Biological Lab, which is down in Solomons, another marine biology lab, part of the University of Maryland. And Dave used to take his lunches, he'd take his lunch break. CBL has a long dock that goes out in the river. Well, Dave would, every day, without fail, he'd walk the dock and he'd count how many sea nettles he saw during the warmer months of the year when they come out. They usually are here June, July, August, maybe into September. So he'd take this walk, he'd count the number of nettles, and he'd take the temperature and salinity of the water each day that he did it. So he did this for 30 years. And Then along comes this young scientist. So Dave was more of, the old-time biologist. He wasn't real savvy with computers and that sort of thing. So enter the picture this new faculty member at CBL, this new biologist. This guy was more of the new kind of biologist. Really computer savvy, knew a lot about statistics, knew what's called modeling. He could model, he could simulate things to see how they would react. So this guy found out about Dave's 30-year data set, and he said, hey, let me see that, let's see if we can figure out, whether we see fluctuations in the population based on temperature and or salinity. And so this guy did his magic on his computer, and what they found was there's a window from the middle of May through the middle of June that is key to whether we're going to have a lot of nettles or a smaller number of nettles. And the two factors, temperature and salinity. If the temperature is above a certain threshold, then we're going to have a lot of nettles. If the salinity is above a certain threshold, then we're going to have a fair number of nettles. The salinity threshold is 10 parts per thousand. Look at these numbers. For almost the whole year, well, that's not true. There were some, no, well, it is. For the whole year, 2018, and for a good part of 2019, we didn't go above 10 parts per thousand. So now you have to look at the life cycle of this animal. The sea nettle has a fascinating life cycle. So what we see in the summer are what are called the medusa. That's a particular, it's almost like a caterpillar metamorphosing into a butterfly. It's the same sort of thing that happens with the sea nettle. The sea nettle starts off as what's called a polyp. Okay, actually there's a stage before the polyp. It's this thing that's attached to a hard substrate, a piling, a rock, something in the water. And it attaches during the winter. Well, when the temperature and the salinity, when the temperature gets above a certain point, this thing turns into a polyp. And a polyp looks like have you ever seen the little anemones that we have in the bay? There are these little anemones called ghost anemones. They look like a little palm tree. Okay, so that's the polyp stage of the nettle. Okay, so now it's turned into a polyp. Now we're getting to the point where those thresholds come into play. Okay, because the polyp, what it wants to do is it wants to produce these things called ephyra. And the process is called strobilation. Okay, so it wants to pump out these little ephyra that will grow into the medusa, the stage that stings us. But in order for the polyp to do this strobilation, temperature has to be above the threshold, salinity has to be above the threshold. So in 2018, we never were above that threshold, so those polyps never did, continue the metamorphosis. They stopped. They were hoping, okay, eventually, I know that salinity is going to get higher, and when it does, then I'm going to start strobilating. But it never got high enough. So that's why there weren't any sea nettles, and there weren't any this year until late. When the salinity got above 10, then boom, these things start pumping out these little ephyra that turn into the medusa. So once again, salinity is a huge factor in so much of the biology of our body of water. And we're going to look at a lot of other animals too in just a minute. Just the fluctuation in this is pretty amazing. This is just a 10-year period. So you can see when we get these high flow events, what it does to the salinity. And now, we were in a drought for July, August, September of this year. And look how quickly the salinity rebounded. So, you know, it happens fast, and it's a vital sort of part of the whole story of the bay and the way the biology works. Okay, so what we're going to do now is we're going to look at a series of pictures of some of the biota in the bay, and we're going to talk about their tolerance to salt. Okay, what is this? Striped bass. Okay. How tolerant is this animal to different salinity regimes?
Pretty tolerant because it can live in the ocean and can spawn in fresh water.
Exactly. What do you call that?
Anadromous.
Anadromous. So this is an anadromous fish that, you know, you can catch out in the ocean, but when it comes time to spawn, this fish migrates up into the tidal fresh portions of the estuary. So this has the full salinity tolerance. We call that a euryhaline organism. You know, it's got the full spectrum of salinity tolerance. What's this animal? That is the American oyster. And how about its salinity tolerance?
Less than the bass because it can't handle fresh.
Exactly. So an oyster, and there's a, oh, did I bring it in here? There's a cool little, oh yeah, here it is. So this is a really cool little newspaper that comes out once a month. The Bay Journal gives you a lot of really neat information, scientific and policy and so forth about the Bay. But look, there's an article on the front page, low salinity wallops oysters in Chesapeake. So it can handle full strength salinity, it can handle down to 5 parts. And once it gets to 5 parts, it becomes really unhappy. Okay? And one of the things that it does, because it's unhappy, is it puts all of its energy into survival, into, you know, just hanging on. And it doesn't reproduce when the salinity is so low. So it's pretty doggone tolerant of differing salinities, but below a certain point, it says, nah, not happy. And that threshold's at about 5 parts. Okay, how about that animal? What is it? What is that?
Bass.
That is a largemouth bass.
Not that tolerant.
What is it like?
Fresh water.
Can it handle any salinity?
Not much.
Just a touch, right? So if I wanted to catch that fish in the estuary, not in a lake or a pond, where would I go?
Patuxent River.
Way up in the upper part of the Patuxent?
Yeah, I jumped there.
Okay. And I hear the Potomac's good too, so that would be way up in the Potomac? Okay, so here's the opposite from, well, here's an animal that can only tolerate a very minimal, if any, range of salinity, largely freshwater. Oh, plants, do they work the same way?
Yeah.
Yep, they sure do. Okay, so this is, the common name of this plant that we're looking at is wild rice. So wild rice is a marsh plant, and there are 2 different kinds of marshes that we have. One is a freshwater marsh, the other is a saltwater marsh. So wild rice, freshwater or saltwater, what do you think?
Freshwater.
Wild rice is a freshwater marsh organism or plant. Okay, so it's funny how plants are the same as animals in terms of their tolerance to differing salinities. Okay, so here's another marsh plant. And this one actually, there was a native form of Phragmites, it's called, and then more recently, an invasive form of Phragmites has come into the watershed, into the bay. This is more of a high salinity plant, although it has quite a range. But it can tolerate a fairly wide range of salinities. But I think it's more of a brackish form of marsh grass. What the heck is that? Plant or animal? That is what's called a diatom. And it's got a really cool name, I think. It's a great sort of Halloween name. It's called skeletonema. So this diatom is, I'm going to use a sort of a big word here. It's a very ubiquitous plant. It occurs all over the world, but it occurs all over the world where the salinity is quite high. It can tolerate full ocean up to about maybe like the oyster, about to 5 parts, and then it's not happy. Oddly enough, there's another species of this genus that likes fresh water. So there are 2 skeletonemas, one higher salinity, one lower salinity. What the heck is that?
Sheldon J. Plankton.
It is. It is. It's plankton from SpongeBob. So that's what's called a copepod. And this is the copepod that we have locally in the summertime. It's called a Acartia tonsa. And Acartia likes brackish water, but it can tolerate higher salinity, but does not like low salinity water. So you're seeing a theme here, how all of these plants and animals have varying tolerances to this sodium chloride that's in the water. The American eel. Somebody tell me about its life cycle.
It's catadromous. It
Catadromous.
spawns out the Sargasso Sea, so it spawns out in the ocean, in the Sargasso Sea, and the little elvers swim back into the estuaries, and then they grow up, and they go back out to spawn.
So, can it go all the way up into fresh water? It can, can't it?
Yes.
Okay, so this is right up there with the striped bass, although opposite directions.
High tolerance.
You're inhaling, right. Okay, what is this in? What is this plant? This is the other kind of plant that we have in the bay. It's called seagrass, or the more scientific name, if you will, is submerged aquatic vegetation, or SAV. So there are a lot of different types of seagrasses in the bay. This is one that can only tolerate fresh water. No, excuse me. It can tolerate fresh into brackish. So we'll find it around here. It's the first one that we see in the spring. It's here, and then by June it's gone. So it's a low salinity, on the full scale of salinities, it prefers that lower end. And you see a lot of it in the early spring in this neck of the woods. It's called horned pondweed, or Xanachelia. So before we go on, I got to tell you another little story. Seagrasses. There was a man, or there still is a man, by the name of Bernie Fowler. And Bernie Fowler is in his mid-90s now. Bernie Fowler grew up in Calvert County, and he was a local politician. He started off, he got into politics, initially local politics, and then he became a state senator. And Bernie Fowler is famous for a couple reasons. and he's also the nicest guy you'll ever meet. But he's famous for a couple reasons. The first is he tells the story of when he was young, he would walk out into the river up to his chest, and he'd be surrounded by lush beds of seagrass. And we have these great aerial photographs of the Patuxent from the 1950s that show seagrass beds all along. Bernie wasn't lying. These photos, corroborate his story. There were lush seagrass beds all along the shorelines. And there are none now. So they got choked out by they didn't have enough light after a while. Too much sediment, too much nutrient, giving rise to all these little microscopic plants in the water. So the sunlight couldn't get down to give them enough to, photosynthesize. So all the seagrass beds got wiped out in the river. So Bernie saw the good, the bad, and the ugly in terms of the health of this river. And when he became a state senator, he sued Prince George's County, Howard County, and maybe Anne Arundel, the upriver counties in the Patuxent watershed. He sued them because they were dumping their sewage effluent into the river, and it was coming down and destroying the health of the entire river. So Bernie was instrumental in getting the cleanup effort started. Let's clean up our sewage treatment plants, number one. So he was instrumental in getting this whole movement started. Bernie's also famous because for many years he conducts a thing called the Bernie Fowler Wade-In. And now it takes place right here at the park. And it's, now it's more of a political, brings attention to the cause. And so Bernie Fowler comes in his blue jean overalls and his white Converse tennis shoes, his old straw hat, and he wades out into the river until he can no longer see his sneakers on his feet when he's standing in the water. And that's the Bernie Fowler Sneaker Index. So the whole importance of this event, it's a goofy event. It's not scientific in any way, but it's politically important. It brings attention to this cause that Bernie has been fighting for decades. So Bernie Fowler, as you can tell, he's one of my heroes. So anyway, see what a little SAV will do to get me started talking about something different. Yes, sir.
Doesn't he still do like 200 push-ups a day?
I don't know if he still does, but up until recently he did. He used to do the Senior Olympics, and he would enter like 5 different events. All these track events, swimming events. Yeah, the guy he was remarkable. He was really amazing.
But he didn't go in with the sneakers this year.
Okay, we're moving on to our friend. Yes, we already talked about this one, so we won't spend much time. Tolerate any salinity pretty much except for fresh and low. How about this one?
I don't blame you.
Diamondback, is that a diamondback terrapin?
They got the cinnamon roll one. I call them cinnamon rolls.
Oh yeah, they do, I see that. That's great. Okay, how about this one? What does he like? He likes medium? Yeah. He can't tolerate fresh, and he doesn't like it real salty either. So it's fun. In the spring, you go down to the beach here, and you'll find nests where they've laid eggs, and unfortunately, most of the time, the raccoons have already gotten into the eggs, but it's neat to know that they're still making nests around here. Okay, so this is sort of a tricky one. Has anyone ever heard of Parker's Creek?
Yeah.
Tell me about it. Where is it?
It's American chestnut.
It's in Calvert County?
Yeah, it's in
Okay, so Parker's Creek, it's a really amazing watershed, a little mini watershed. And one of the amazing things about it is that it's been totally protected, or quote unquote, totally protected. All the land bordering this creek has been bought up, no development, no houses. They were going to build a golf course at one point in this watershed. No golf course. The only bad thing is the headwaters is the Prince Frederick sewage treatment plant, but oh well. But as far as land use, it's the only real pressure directly on Parker's Creek. But one of the other cool things about Parker's Creek is if you take a canoe from the mouth of Parker's Creek up to the headwaters of Parker's Creek, you're paddling through this sinewy creek through these different marsh systems. You start off in a salt marsh, and you end up in a freshwater marsh. And there are two different types of cattail. In the saltier marsh, I think it's the broadleaf. Once again, there's one type of cattail. I think it's the broadleaf. And then when you get up into the saltwater part of the marsh, there's a completely different cattail. So this is sort of a trick question here. Some cattails like it salty, some cattails like it fresh. Okay, so this, we saw the wild rice, and this is the opposite end of the spectrum. This is Spartina alterniflora, probably the most important plant in the bay. It's the primary salt marsh plant. It's great for stabilizing shorelines, great for habitat, and these marshes act as filters. They're right up there with the oyster in terms of their ability to filter bad things from getting into the bay. So this guy, high salinity. Another kind of seagrass. This one is called eelgrass.
Yeah.
It's also, I like the scientific name of this one too, it's Zostera. So eelgrass is a high salinity submerged or seagrass. And one of the, just to show you that not only salinity is an important factor in controlling different plants and animals, but temperature is as well. Back in, I want to say 2012, we had an abnormally hot summer. And this eelgrass grows in high salinity water, so it's mainly down in the Virginia part of the bay, maybe completely in the Virginia part of the bay. And during that really hot summer, we had a huge they had a huge die-off of eelgrass. And it was driven by the water temperature, not the salinity of the water. The water temperature got so warm that this thing couldn't take it. And we had a huge die-off of eelgrass in the Virginia part of the bay. Okay, we're getting near the end. These last two are different kinds of fish, opposite ends of the spectrum. So this is the channel catfish. Okay, my fisherman buddies, what is this one like? Salt, fresh, in between. Channel catfish.
More like fresh, like.
Ben, what's your answer?
Like, I caught him.
Like top of the
Like, it doesn't really want to go in the bay.
It likes lower salinity, doesn't it? Fresh,
A little fresh.
a little bit of salinity. So what about there's a bad boy that's come into the bay.
blue.
The blue catfish.
Yeah, I'm catching them everywhere.
It can tolerate a pretty wide range of salinities, can it? Darn it. Darn it.
Any size.
Yep. Okay, so there's that low salinity tolerant fish, and this is another cool fish that we have in the bay. It's called the northern puffer. And this is the opposite. it can tolerate high to moderate salinities, but it doesn't like low salinities. It's a really cool fish. Sometimes we catch them in our crab pots. We have a crab survey that we do every year, and we'll occasionally pull up a northern puffer in our crab pots. They're neat little fish. Okay, so hopefully I haven't exhausted you with this concept of how important salinity is and how it changes, and how different animals and plants react to different levels of salt in the water. Yes, sir. See the fishies? That's next time. Sorry. Next time. Okay, any questions about any of this? I think I've lost those guys. Okay, we're going to move next door now. So we can leave all